little bit of a diversion, which is not going to be important for any of the rest of the lecture. And the diversion was just to kind of introduce you to this idea of topological insulators. So if you remember, we had the following situation. We were thinking about a rather different setup where you had a system with a lattice. And when you have a lattice, the momentum space becomes compact. It becomes what's called the Brillouin zone. So the momentum space, or the Brillouin zone, is a torus. And every point on this torus labels the possible momentum of a state, which means that at every single point there's an associated state. It depends on the momentum k, which by Bloch's theorem you can write in terms of some phase factor depending on momentum, and then this periodic wave function. And then there was this beautiful claim. The claim is that you define the Beres phase. Beres phase over the Brillouin zone by taking these wave functions uk and differentiating them with respect to k. Okay. So this Beres phase is somehow capturing the way in which these states wind, or the phase of these states winds as you move around this torus. And then the lovely result that we ended with is this result due to TKNN. So the TKNN formula is the following. It's that sigma xy is e squared over 2 pi h times the sum over all filled bands, C alpha, where C alpha is the Chern number, and the Chern number just means the integral over the Brillouin zone of the field strength associated to this point. Okay, so this is the formula that I wrote down. And what I planned to do was derive this, was just go through and prove this from everything we had. I can still do that. I think what I'm going to do is take a vote, actually. Let me tell you the pros and cons about why we should or shouldn't derive this. The reason we should do it is because this is extremely important. This is really the basis, as I said, for everything to do with topological insulators. And you can kind of see the essence of it here, that you have this Brillouin zone, and every state in this is filled, so you're in an insulating state. But nonetheless, there's interesting topology associated with these insulators coming from things like how wave functions wind around this. And the whole subject of topological insulators that's taken off in the last 5 to 10 years has really been classifying the different kinds of topologies that you can have in different dimensions and with different restrictions and symmetries on the states. So this is the simplest example. So it's very important, but it's very important for a subject that's a little different from what we're doing here. It's very important for topological insulators. So that's the reason to do it. The reason not to do it are one, it's kind of just messy algebra, and it's going to take about 20 minutes, and it's kind of horrible to lecture messy algebra. Two, it's in the notes. And three, we're not going to need it for anything that follows. This is really just kind of a so it's entirely up to you guys. I'll take a vote. Who wants me to lecture messy algebra? That's the director. How many votes does the director get?
He's mentally challenged to do algebra.
Who doesn't want me to lecture messy algebra?
How about the middle ground, which is that if you could just sketch the steps if that's possible.
I mean, partly I'm saying this because I only understand what's going on if a little bit of the algebra is sketched out, so maybe not all of it.
Let's.
Well, for example, is the proof going to hold despite disorder and so on, which you emphasized is so important, David, in the last talk?
Yes. Yeah, the proof, because we're not, it's very general, everything I'm saying here, right? All I'm insisting is that every single state in a band is filled. That's the statement that we're an insulator. Other than that, these wave functions can be anything you like. They can be wave functions in the presence of disorder and the absence of disorder. Magnetic fields, no magnetic fields. The requirements are 1, Brillouin zone, 2, all states filled. That's it. So it's a very, very general result.
I see. And
so you need the torus.
You need the torus. You need the tree of Brillouin zone.
Yeah, you still.
Can I ask? I'm sorry for being so remedial, but with disorder, usually one may not even work with momentum, eigenstates, and so on.
That's
then.
You still need the torus somehow.
Yeah. the torus should still parameterize the states.
States, okay.
Yeah, it doesn't have to be a conserved quantum number anymore. That's not going to enter the proof. But the state should still be parameterized by the torus, so you can still define this object. Let me sketch the proof. The trickiest part is by far the first line, actually. So let's let me remind you about the formula I also didn't prove. The formula I also didn't prove was the Kubo formula. And the Kubo formula is the formula for the conductivity. The proof of this is proof, so you can just check this. The hard part is the next line, which I'm just going to write down. The reason it's hard is the following. These states here are multi-particle states, which means that when I write this simple 0, you have all of these particles, each of which is filling in the ground state every single possible state in this. So this simple thing that we write here 0 is shorthand for something very complicated. It's all the states in a band filling. Now this Berry phase is written in terms of single particle states. So the hard part of this proof is just rewriting this simple shorthand formula in terms of something more complicated that involves single particle states, which I'm just going to write. So I'm going to write it down in a way which it's so messy that this is kind of the best compromise I can come to, but I'll try and explain what's lacking in the notation that I'm writing. So, the claim is that the Kubo formula, when written in terms of single particle states, takes this form. So let me sort of walk you through what's going on here. You can see the general structure is the same. It's some state, current, some other state. That hasn't changed. What's changed is the sums and the intervals. So this is the sum over all states which are not equal to the vacuum state. All multi-particle states that are not equal. So what are all states? So each single particle state has two labels. One is the band, which are in, and the other is the momentum of. So what we're doing here is to sum over all states. We're summing over all possible bands. And we're summing over all bands, but I'm distinguishing them. Bands labeled with alpha are bands that are filled in the ground state, and bands labeled with beta are bands that are unfilled. The Fermi energy sits in the middle to distinguish. So you sum over all of them at this stage, but there's two different bands. And then you integrate over the single particle momenta, and that's summing over all the different states within the band. What's bad about this is that there's no reason that the momentum for the particle in alpha should be the same as the momentum for the particle in beta. So there should really be a prime here and another integration, and I just dropped it for having finite space. That's the hard step of the proof. You're just convincing yourself that this is the right way to write this formula in terms of single particle weight functions.
So, David, one thing is what Sandeep asked is about whether momentum is a valid description at all.
Yes.
The other one is that, so one is assuming that whatever the interactions is, that there is some kind of Gaussian particle in terms of which you are writing these.
I don't think so. So what am I assuming? I'm not assuming momentum is a conserved number. I'm just assuming that states can be labelled by the torus. So for example, suppose there was no disorder, then we know momentum is a conserved number. Now add disorder, And just think about this Hilbert space of states is going to deform in some way. You can still label the states by points on the torus. It's just that number's no longer a conserved quantity. So you can think about the K just as labeling the states.
But how about the single particle description at all? So the other question is about interaction.
Oh, sorry, this is only valid for single particles. That's right. It's for non-interacting electrons. Yes. That's important.
So, if you have interaction, then you were saying that there will be some quasi-particle description still valid or not.
To my knowledge, no one knows how to generalize this in the presence of interaction. It's not clear.
David, if you have disorder, you still need exact lattice periodicity for the Bloom zone to be a torus, right? Don't you need lattice periodicity to say that you have a torus?
But you don't mean the lattice is periodic. You mean the disorder is commensurate with the lattice in some way.
I mean that lattice translations must be a symmetry for you to say that the states are
labeled by the Brion.
Bloch's theorem has to hold, right?
I think that's true. I was thinking about some type binding approximation where
it's disorder only on lattice points.
Exactly.
Potential only.
That's what I had in mind. Okay. But yes, you're right. Okay. Other questions about this?
So just so I understand that, I thought it's enough that your states are labeled by these parameters, the momenta which lie on a torus.
Yes.
And that's not enough. And then the disorder, shifts around what the energy.
They lie on a torus because shifting the momentum by 2 pi over a is not doing anything.
Yeah.
But that's only true if you have exact lattice periodicity in real space.
You're saying disorder could break that.
Here's the counterexample. Imagine a free particle moving in the continuum, but in the presence of a periodic potential. So this falls into this category, even though it's a continuum. And now put disorder on top of that. The disorder has to have the same periodicity as the
That's
lattice,
a very
otherwise
restricted.
this picture breaks down. But what I really have in mind here is something more like hopping.
You have a lattice
hopping
model.
on lattice. And then as long as the disorder is site by site,
It's okay, yeah.
it's okay. Okay. Any questions about this?
There's a version of this which simply doesn't use the lattice as such, but just places the whole thing on a torus and says states can be leveled by things on a torus.
There's another version which is in the notes that I haven't done, where you place the system on a spatial torus in the continuum, and then there's something related to this, although it's conceptually it's not as clear how that works. You have to pass fluxes through various.
Sorry, just in that formula, so the ground state is just all the bands occupied, all the states occupied up till EF.
That's right.
And is that what that UK alpha stands for then?
UK alpha are the bands that
Are filled up?
Exactly.
Okay, so I understand. Just zero becomes in this one particle non-interacting picture.
Okay, so the next thing we need to do is come up with some expression for the current. The way we do that is we think about the Hamiltonian acting on these wave functions. So this is the Schrödinger equation. And we rewrite this as eta minus ik of x ik of x times uk, which is this block wave function. So it's just a Schrödinger equation for the block wave function as opposed to the psi, and everything that's in here we call h tilde f. By the way, Gautam, in the last lecture you pointed out that the Berry phase here is conceptually a little bit different from the usual Berry phase because you're varying with respect to the label of the state as opposed to a parameter in the Hamiltonian.
Right.
If you write it in this form, it becomes the same as the usual way because now K has just been incorporated as a parameter in the Hamiltonian. So the current is J is E over H bar H tilde by dk. Okay, so why is that? It's because this is the group velocity. It's the variation of the energy with respect to the momentum is the group velocity, and the current is roughly mass times velocity. Just to check, let's look at something very simple that we've seen before. Suppose that what we have is a Hamiltonian, not for a particle on a lattice, but just a free particle. This should be true regardless of whether the particle is a lattice or not. 2n p plus h bar k plus ea squared, which means that j is e times x dot, where x dot is the thing that p is n times x dot.
Sorry, what do you mean? E plus h? E mean just one of them, not both p and exactly. Right? Or
P being d by dx.
Oh,
so
okay,
I replace
okay.
P with id by dx.
I see.
And okay, so this definition agrees with the definition we were using previously if you apply it to the Hamiltonian we were using. So I just want to say it's a good definition. Okay, so what do we do? Everywhere that there's a j, we replace it by dh by dk. And we'll leave that up there, actually. So now we get terms like uk alpha di by dh tilde uk beta. Okay? Replacing the j's with this. And we just rewrite this as uk alpha di h tilde times uk minus uk alpha h tilde di uk beta. Okay, uk alpha is perpendicular to uk beta. Because they're different values. So I can take this derivative acting on here and turn it around and act it. Okay, what I'm really saying is uk alpha, uk beta is 0. If I differentiate that, this derivative acting on here. So, actually, let me do this. Give me 60 seconds before you ask questions. Okay. Minus e alpha k. So that's the statement that's made. And it looks naively as if there's a term that's missing. That's the claim I want to make. This expression here is equal to this expression here if you use the fact that this vanishes, because they're different values. Okay, is that clear? Let's see. So this term here is obviously the minus e alpha k, because the h can act this way. This here is obviously e beta times u. So when I differentiate it, you might expect there's two terms. There's this term. But you might expect there's this extra term here, but that vanishes because the orthogonality. So that's the key step. So now we're left with still summing over all possible bands. As I say, if you do this properly, you have to take care about certain delta functions because you're supposed to be integrating over different momenta on different bands. They'll just work out. You have to trust me on that. Do it yourself. is what we get. And you can see that what's going on is the denominator, which was the difference in energies squared, that's cancelled. That's cancelled because rewriting these terms with the currents comes with difference of energies. There's two of them, so you get a difference of energies.
By del y, you mean del ky.
All derivatives with respect to momenta rather than space. Okay. The final step is to notice that we're summing over all bands here. But the things in the middle are the unfilled bands. And summing over the unfilled bands, again, this is a little bit schematic because I should really be including some of these. So this is just the statement that if you sum over all possible states, you get the identity. This is the insertion of the identity. Unfilled bands, filled bands. But this sum over the middle is over the unfilled bands, and I plug in this. The sum over the filled bands vanishes by symmetry. Okay, these two terms cancel. So this term vanishes by symmetry. And we're left with sigma x y is I e squared the sum only over the filled bands. And the integral of the torus dy uk alpha dx uk beta minus sorry, no betas, everything's alpha. And if you look back, this is precisely the integral of the field strength. So that's by the way, if you want to read more about this, whatever you do, don't look at the original paper by Fox. There's a disease in condensed matter physics. I'm sorry, you guys. You're so desperate to publish in a PhysRev letter that all the papers are completely incomprehensible. So who can write anything in 4 pages with stupid thing comments? So if you want to read this, there was a nice review article by Kohamoto, who was one of the original authors, that came out sometime in the mid-80s, and I think that's the best place I found at least. By Kohamoto. The TKNN stands for Doubtless Kohamoto in 1980.
Sorry, David, I missed one step.
Yeah.
So I got up till that line.
Which one? This one.
This one. And then the sum over betas you write as 1 minus that. That
yes.
minus term cancels.
That minus term cancels.
And then you're left with the 1. But then, I'm sorry, but why does that give? So shouldn't that give bra whatever del y u? Oh, okay, I got it. Thank you.
Yeah. Good.
There is probably one more review article by Qian Niu.
By who?
Qian Niu, NIU.
Oh, yeah, he wrote famous follow-up articles with Alex about on the torus.
But then he has reviews of modern physics where he uses these and topological insulators.
Oh, I did come across it. Yes, that's right. Yeah.
It has some of it, not all the details. But
called Berry phase and electronic systems, something like that.
Something like that.
Yeah, well, that was.
Sorry, going back to this comment you made about lattice system and disorder on lattice point. Can you just repeat what you said? I mean, does this go through there, you're saying? Or what did you say about lattice system?
I think if I just have a lattice system with
disorder on the side, potentials on the side.
Yeah, there's no potential on the side.
That are random.
What would not go through?
In the presence of the lattice potential, correct me if I'm wrong, the lattice translation vector is no longer a symmetry, right?
If you have different disorder on...
random potential, right? So every site has a different energy epsilon.
That's true. Yeah.
So what is the statement actually?
So what do we need? We have a bunch of bands and there's a gap between the bands.
That part goes to.
And the bands have to have some kind of topology in the sense that...
they need to have some topological invariant you define, right?
Yes, they need to have some topology themselves, right. which follows in the presence of a lattice because of, as you point out, because of lattice transformations, which ensures that k goes to k plus reciprocal vector is the same.
Is this in the same class where of arguments where you say that you have a topological invariant,
Yes.
and at least perturbatively in disorder, I can put in disorder and this will not change my. It's a local addition to the Hamiltonian.
Yes.
As long as I'm not closing gaps.
No, so that argument is good if I know how to write that invariant down in a formula that works
You need
for all
to-
sorts of states, right?
You can't close the gap, but whatever assumptions you put in, you have to also hold. And one of the assumptions was that the Brillouin zone describes.
Yeah, so I mean you need a formula that will work for a general single particle wave
That's
function.
true. That I don't know how.
This one seems to work for block states.
Yeah, I mean, isn't it important that you are labeling the state by momentum in the end? Because the current was del H over del K, right?
Yes, though it didn't have to be conserved.
That's true.
It didn't have to be conserved momentum, but it had to be that topology of the Brillouin zone.
But I mean, more specifically, doesn't it have to be related to translations? I mean, somehow the label that labels the states seems to be crucially tight.
That's true.
That'd be
But the
huge,
question is
yeah.
translational invariance.
Yeah, and even if translational invariance is broken, you say.
So actually, I take it back. I don't know. Is the answer.
But you're right, people certainly talk about disordered systems and compute Chern numbers in numerical calculations. So there must be some other way of doing that.
But this one, I don't understand. I mean, if the disorder is very high and the states are hugely localized, can you still meaningfully label them by momentum?
No, but by Chern number you can.
So your number a lot then, because you're not characterizing the set of states by some momentum label. It seems very.
Yes, that's what I'm asking.
What's really meant by what's really meant by this? What you mean is that there's a state here, and it's close to a state here. You can write down some kind of metric on the Hilbert space. And what you mean is that this state here, you can move in some way, and if you move in some way, you get back to a state that's again. But that kind of topology sounds to me like that should be robust under small changes, not just the existence of a Hilbert space with this underlying topology. So it sounds like it should.
So you think K will not be momentum, but will be
Some
some
other
other
way.
continuous.
Yeah.
If we momentum, then J will be interested in
Well, it can
conductivity.
still be momentum, just not conserved.
Could it be that you actually take this lattice and wrap it around in two directions, and then modify the Hamiltonian by adding
It
fluxes?
can't be any label.
That's the other.
It has to be momentum.
So that one will still give me a formula with or without disorder. Because that's just sensitivity of single wave functions to twist.
That's right. So that's true even in the presence of interactions.
Yeah, but
You don't need to-
particular for the non-interactive problem, I can take the single particle states with disorder and get a formula.
That's absolutely
that. So is that equivalent?
Which one, the Loveling argument?
This?
Kedar, are you talking Loveling argument?
Yeah, no,
Yeah.
of course, it
Yeah.
gives the whole conductivity. So if you start,
So
typically
yeah.
you're starting the different systems. Yeah.
So with disorder, maybe that's the version that generalizes.
Actually, that's not even true, no?
No.
If I think of it as random potentials,
Yes.
then where is my rotational symmetry which lets me talk about angular momentum?
No, it's not.
No, it's not angular momentum.
Sorry, just so everybody follows, I should tell you what's
Sorry,
going
yeah.
on. There's a separate way to talk about Chern classes associated to whole conductivities. And what you do is the following: you take your system, continuum or otherwise, and you put it on a spatial torus. So space is now a torus.
Then you can.
But that's not the torus of interest. But what you then do is you thread through this side of the torus some flux, and you thread in the middle of the torus
A second flux.
something. So through each of the cycles of the torus, you thread two fluxes, phi1 and phi2. Now, by the kind of arguments we were talking about using spectral flow, the parameter space of those fluxes
That's your torus.
is a torus.
Yeah.
Because each flux varies from 0 to phi0, and then the spectrum returns to itself. So now you have a new system where the parameter space is a
these-
torus.
yeah,
It's
now
the
this
parameter
will
space
work.
of possible fluxes. Now you can compute
This
the very
works with
phase-
disorder or without disorder.
Yeah, now you can compute the very phase associated to those fluxes, and integrate that
Exactly.
field
So
strength.
I think in numerical calculations with disorder, that's what people would do.
Please explain again. Sorry, I understood one of the two fluxes which was going.
There's two holes, right?
So an alternative approach.
One is
Well,
going along
there's
the
two one cycles on the torus.
That's right. So you thread a flux
But
to each.
you can't thread a magnetic flux to a one cycle.
No. So there's two periodic directions.
So what do we mean by the flux?
You just mean a phase along the one cycle? Huh?
Yeah, that's what
Twisted
Oh, okay. Twisted boundary condition.
Twisted boundary.
Oh, okay. Fine. Then I understand. Sorry. Just trying
So
to-
two twists with periodicity in the space of twists.
No.
Okay, so there's phi 1 and phi 2. And
That's
the
a
parameter
torus.
space of phi 1 and phi 2 is a torus.
Okay, I got it.
And there's a similar formula for sigma xy in terms of derivatives with respect
Wave
to
function
equations.
d by d phi I.
What do you mean by parameter space of the flux? Can you explain?
And then compute the Chern class of this over this torus. That's also equal to the whole conductivity.
What's chi and what do you mean by parameter space of the flux? Can you
The phi is
the chi, whatever you mean.
sorry.
And
This
what
psi,
Yeah.
this is just the ground state of the system, defined on this torus in the presence of these fluxes.
And I guess in the case of the periodic system, the two are the same because when you thread a flux, you shift k by the flux. So derivatives with respect to the flux are the same as derivatives with respect to k. So that's the two formulae are the same. So you can rewrite this formula in that language and then generalize to disorder.
What are you doing? You have a flux through the middle, magnetic flux or whatever, and what is this other?
So there's a flux through the, you have your donut, and through the center of the donut where the bread should be, you put a flux. Okay? Everything's living on the surface. And then through this cycle, you put a flux.
So maybe I can say this again. Operationally, at the level of the Hamiltonian, you write down a Hamiltonian, and then you're looking at states that obey some twisted periodicity condition when you take x to x plus L, and another twisted periodicity when you take y to y plus Ly. And those two twists you can choose, so you get different problems for different twists. So that's.
So this calculation showing that the Chern class of this also gives rise to the whole is also in the notes. It's both more powerful and I think a little more suspect as well. It's more suspect for the following reason, that you prove that the Hall conductivity averaged over all possible fluxes is quantized. And that just strikes me as a little bit odd. Because you're not computing it averaged over all fluxes, you're computing it ultimately with phi 1 equals phi 2 equals 0.
Yes.
So that's one of the reasons I didn't present it here. I'm sort of a little uncomfortable about that part of the argument. The textbooks say, oh, but actually when you measure it, condensed matter words doesn't matter. I didn't understand those condensed matter words, so I just kind of... and I honestly can't tell if they're serious or if they're just making it up.
But isn't it at least true that this formula I could rewrite in that language?
I think what Kedara says that if you have a lattice and it's periodic, right, so this donut is itself a lattice, then I think the two formulae agree with each other. So I think there is an equality there. This formula is more powerful though because we don't put single particle states here. So this formula holds no matter how strong the interactions are between electrons.
Actually, that's what I was going to ask. But isn't that too powerful?
Yes, yeah, because in about 3 minutes' time we're going to talk about the fractional quantum Hall effect, and this formula says that you can't possibly have a fractional quantum Hall effect. But there's an assumption, and the assumption is that there's a unique ground state when you put the system on the torus. And the way the fractional quantum Hall effect gets around this, as we'll see in lectures 2 or 2 time, if you take a fractional quantum Hall state and put it on the torus, you do get degenerate ground states. This is an example of topological order.
Just one more remedial question, sorry. When you wrote that form of the state, that psi was e to the I k dot x times u of k. Sorry for being so remedial, but once you have disorder and so on, that seems like more of a momentum eigenbasis.
Bloch's theorem requires this lattice calculation. maybe I take it back. It's true that the TK formula is only valid for pure lattice systems, not using it.
In fact, it is a good point now because you have in your proof you have used that those things are eigenstates. The log states are actually eigenstates of the Hamiltonian.
Yes, sorry, you're completely right.
So therefore, K has to be a good quantity.
Yeah.
Yes.
So all I'm saying is you presented a very beautiful argument in a consistent way if K can label the eigenstates. But then maybe once disorder at least becomes big enough or something.
As soon as you put on disorder.
But again, I don't know if it's small.
So alternatively, you can make an argument that it's some topological invariant, small perturbation, unless.
Yeah, to make that argument, you'd first rewrite this formula in that other language. And then make that argument.
So it sounds like we've come to a consistent picture. That this TKNN formula that we did with a lattice is not valid in the presence of
at least strong disorders. At least strong disorders.
No, I think even weak disorder. It sounds like
because
it sounds like we needed momentum.
Lattice translation.
I'm saying this disorder you can't put this on that.
Lattice translation.
We don't get a Riemann-Zobel.
And there's one step here which will not work.
And as Gelson pointed out, we actually did assume.
Yeah.
Although I didn't realize.
When you said h of that UK,
here. This very notation is assuming the K is a conservative.
I mean, it's something we assumed even before because the QHE formula assumes that you are working with the eigenstates of the Hamiltonian.
Yeah.
No, I thought there was some thinking that because that you could still write the states as e to the ik, right? It's because when you go one entire lattice bend to end, you come back with a phase of 2 pi.
Yeah, but these were energy eigenstates. So I think that the lattice system, you need that to be no distinct.
No, there you could still have an escape route because those are energy eigenstates of the whole, the full many-body Hamiltonian.
Yeah.
And these En and E0 are, but here, right. So when you come to that thing,
I think that's right. Okay. So this other formula, which I think is due to Averron and Seiler, although everybody always calls it the TKNN formula. Although I don't think it is due to TKNN. This is valid with disorder with arbitrary interactions. So there's these two different approaches. But everything's pointing to the same fact that there's topology underlying the quantization. That's really the key lesson.
So what's the reference? Averron and who?
I think it's Averron and Seiler, S-I-E-L-E-R.
Can I ask one more really dumb question and I should ask you later, which is, I mean, physically, when you are trying to, you take one of these systems and you're trying to measure the Hall conductance, can one ask meaningfully whether the current is going through the bulk or is it a surface effect? That is, I mean, it seemed some part of the story is tied to the fact, the robustness is tied to the fact that it's a surface effect. But our derivations don't use that so much.
I can tell you. So I can tell you what various things I've read in the literature. I've read places in the literature where it says this is entirely due to the edge currents, and there's some nice lectures by Leggett, actually, Tony Leggett, who says lots of places in the literature claim this is due to edge currents. I think this is controversial. And when I looked a little more closely, so I didn't explain the edge currents here, but they're in the notes, and I may explain them towards the end of these lectures. You can do a calculation where it looks as if it's due to the edge currents, and then if you look a little more closely, you see actually it's not. The calculation that shows you it's due to the edge currents, actually you can get contributions from the bulk. It's just the bulk terms all cancel out and leave you with only the edge currents. So I think it's not true that it's only due to the edge currents, but I've never actually measured this thing. So.
No, are you saying that is it not true that is it true that there are bulk currents or the conductivity even in that calculation?
Do you know this? I don't know if you know this. So here's a cross section in a random potential. Okay. And the basic idea of these edge currents is that if you remember, we're going to assume this potential is large compared to LB. Which means that you can just take the wave functions in the absence of disorder and just think about them as sitting here. Now, the momentum K in the y direction turns into the position in the x direction. That's one of the things we saw in the Landau cage. Which means that actually, usually in Fermi surfaces you think about building things up in momentum space. Here it's quite nice. You think about building the Fermi surface up by populating things in real space, because momentum in the y direction is the same as position here. So you just draw dots every LB distance. Okay, these are the states, and you fill these states. So you fill all these states. And then let's put a difference in a chemical potential to try and induce a current. So these are the Fermi energies, which are going to be different here and here. Okay, so there's some potential difference, delta mu. And the question is, what's the current in this setting? So the current, that's basically what we've computed here. It's Jx is it's basically dV by dx. For the same reason as this group velocity. So the total current, sorry, I think that's Jy is dV.
Yeah, because it's dV ky.
Ky is the same thing as dV. So the total current on y is basically the integral over x with thin constants of proportionality that I'm missing of dV by dx. Which is the difference between here and here. Is delta mu. And of course the proportionality constants that I'm missing should work out to be the conductivity, which is quantized to be 1 and constant does. So the way people usually argue that there are edge currents is they say, well, look at the following potential. You fit all of this, these should be dots. And the difference, all of this is coming from the difference between here and here. So you can think about just the terms on the edge as contributing. But it's not true, because if I look at this potential, you can see that, there's currents everywhere along here. But they're cancelling each other out precisely because when you integrate it's a total derivative, so you only get the edge contributions. Does that sort of make sense?
You think the currents going like this and going like that, and overall they cancel?
Yeah, they just cancel.
They are there.
But it looks like they're there, at least in this very naive. By the way, this is my take. Didn't read this in the literature anyway, so I may have made a mistake. But it seems to me that this is what's going on. All right.
So when if the disorder is away from the edges, then all you need is that the key is a good description and near the edges, and in the middle some stuff is happening, but the key is a good description here, the key is a good description there. I think it's that may work.
Is this the case number?
I think we've got so many geometries going on. We had an annulus, and we had a lattice, and we had a spatial boundary. And I think the answers to these kind of questions actually depend on exactly what setting you're looking at. It's pretty obvious if you have a spatial torus, the edge effects aren't doing anything because there's no edges.
I always got confused between these two statements. One, that the Hall effect arose precisely because most states are localized, but some are extended in the bulk.
Yes.
And that suggested that the current is then carried by those extended states. And on the other hand, the fact that it should be a surface effect.
Well, one way to reconcile them, if you have the right kind of geometry, is that there's always extended states at the edge.
So it's extended states at the edge will do it, not in the bulk.
But in the bulk will let you go from one plateau to another.
But I think generically, if you have some states in the middle of what was the Fermi band,
so the point is, if you actually have bulk delocalized states, you will not see this nice plateau. You will be in the transition from one plateau to the
other.
I
don't think that's quite a true statement. So we have this picture, and these are the
in the middle there's extended states, right?
And these can be the extended states which are in the bulk.
Yes.
If our Fermi energy is here, these states are filled.
Right. Yeah, so they don't. Yeah.
But so they are contributing to the conductivity.
I thought that was the point. They are contributing as much as if the Fermi surface were right there. They are going up, but they continue to contribute. That's why you get that.
But they're not contributing yet. Yeah, Yes. So I think this is another way of saying that it's not just the edge that's contributing.
Yeah.
But when you're talking about the
It's 0 to 1.
when you're sitting here,
0 to 1,
the populated ones are changing.
Yeah.
Yeah. But I had exactly this in mind. That suggests it's just the bulks.
Right.
But of course, it may be that there are no bulk extended states.
Okay.
There are only edge states.
Okay.
In which the whole conductivity is the same regardless. Right? That's the disorder not engaging very time.
So I would have thought that when you are sitting there, that's at the middle of the plateau, and you can come off half the plateau and hit
So I
that
think
edge
the point
state
you're
of the-
missing, which he's making, is that sigma xy is not a Fermi-surface quantity.
Sigma xy.
And so the bulk way of thinking about it is what Sandeep is talking about. Saying if you're there, then everything below it gives 1, 1, 1, 1, 1, and that's the integer you see on the plateau. Right? So in that sense, if you take that literally, it's the bulk states that deal with us, right?
Yeah. Exactly.
But I think this is the same kind of picture as pretend that your potential's like this, and you fill up, or pretend that your potential's like this,
And you fill up.
and you fill up. Here, there's no bulk things contributing because dV by the x is 0 in the middle. And here, there are bulk things contributing, but they're cancelled out. So I think the same story must be true.
Mm-hmm.
Must be true. All right. We're going to do the fractional quantum Hall effect next. There's some good news. I think this is going to be less controversial for the following reason. It's much, much harder. But in a way that means all of these kind of attempts at precise calculations that we've been, not a chance. The fractional quantum Hall effect. So instead, it's kind of amazing. I'd say that there's a very, very good idea of how the fractional quantum Hall effect works. But a large part of this is just by very clever people making leaps of intuition about the way it probably should work, and then that's turning out. We'll see that in a few examples, at least 2 cases. As we go on. So, in the fractional, in the integer case, I really tried to derive everything starting from the first principle. That ain't going to happen. We're just sort of going to make leaps, and then we'll spend a lot of time just checking that those guesses stand up to scrutiny. So it's a slightly different style of physics than if you do string theory, we never do this. We're so precise about everything. I think we need to be a bit more bold and adventurous. So the kind of things that worked here, we should be a bit more creative sometimes. Okay, so section 3. And it's the fractional quantum. Okay, so what do we need to explain? We need to explain the fact that rho xy, which is 2 pi h bar over e, times mu. And we've just spent a couple of lectures arguing in various situations that this object mu has to be an integer. And in fact, it's not. So from experiment, we know that this contains fractions. There aren't any old fractions that appear. There are very specific fractions that arise. 1/3 is very prominent. 2/3 is very prominent. And then as you make the samples cleaner and better, or you go to stronger magnetic fields or lower temperatures, you start to see other fractions, but the other fractions tend to appear in very specific orders. So 2/5 is prominent, 1/5, if you're in a suitably high magnetic field, is prominent. 3/7, 4/9. And then a whole slew of fractions. I think there are about 80 different fractions that have been seen in various quantum Hall systems.
Okay, so put these fractions in some series or?
Roughly speaking,
some
some series, and we'll start to see how this arises.
the theories that you are talking about, are they able to predict new fractions that you should see, and then
yes,
fragments
and
solve
some of
those
those
new
predictions are work better than others. But there is now a setup due to Jane, something called the composite fermion approach, that basically gets the fractions in the right order. And we'll see this in about 2 or 3 lectures. And then there are some weird fractions that don't really fit into this. 12/3, 5/2, 5 halves actually fits in some interesting way.
12
thirds.
Sorry? Sorry, no, did I say that right? 12 thirds or 13? Sorry, 12 thirds is 4. 12 fifths. That's better. Yeah, 12 fifths and 13 fifths are interesting and don't quite fit into this picture. It's complicated, but you know, a large part of this has been proposed. Okay, so what's going on here? The number of states in a Landau level. I've realised I've got capital N written here, but capital N is going to be the number of electrons. So we'll certainly call it N2. It's early N2. So the number of states in a Landau level is A times B divided by 5. And the important point is this is a very, very large number, because A is the area of your sample. A is something macroscopic, maybe it only be a millimeter, but this is a very large number. Meanwhile, if you're in one of these fractions, this from what we've seen before is the fraction of states in this lowest Landau level would have been filled. So if you're in the fraction nu halves, it means that 1/3 of these states have been filled. So we're filling nu less than 1 of these states. And the number of ways to fill a fraction nu of n tilde states is the following. So this is the number of single particle states, but once you've chosen to fill that number of electrons, then this is the number of multi-particle states in the system, because this is the number of ways you can that many states. This is a huge number. This is an exponential of n, and n itself is something like 10 to the 11. So this is an exponential of an exponential. It's a very, very large number. So this is the number of states that we have. All of these states are degenerate, because everything in the lowest Landau level is degenerate. So this is big. Now let's add interactions. And we'll assume that there's no disorder for the moment. The most prominent interaction between electrons is simply the Coulomb force. So we know that at the very least, electrons experience some kind of Coulomb force. Notice that in this situation, there's no such thing as weak interactions, because you've got this vast degenerate Hilbert space, and any interaction you put in has to break that. Okay, it has to break that degeneracy. So there's no small parameter. It's because kinetic energy has been completely quenched in the lowest Landau level. Usually the small parameter is potential energy divided by kinetic energy. There is no kinetic energy. So any interaction, you can't make E squared small to make this problem solvable. Whatever this parameter here is, this is going to be the dominant thing. And if you want to do perturbation theory, you need to do degenerate perturbation theory. But where the kind of matrices you need to diagonalize have dimension exponential of an exponential. This is a very degenerate perturbation. So it's going to be hard. Okay, so what can you do? You could do this maybe numerically. People spend a lot of time trying to diagonalize this numerically. You can do that for, as far as I'm aware, up to about 16 particles. Okay, that's state of the art, is that number of particles. But you want to do it for 10 to the 11. And this scales exponentially. So we're not going to get there by solving this even numerically.
I'm sorry, David, can I ask? I mean, all these comments are, of course, equally true for the integer quantum model, right? I mean, that, if we have some magnetic field and generically given, we fill out some of the Landau levels, we have a huge degeneracy, etc., etc.
But there, the integer part meant you were always in a system where you filled up all the states.
You filled up all, but now you're looking for the plateau phenomenon, the fact that you continue to get the plateaus. And there, you're not filling out all the Landau
So I think what's going on here is the integer, you're really in the regime that this, which is the gap between Landau levels, is much bigger than the energy of disorder, which in turn is much bigger than any interaction energy between them, so you can just ignore the interaction.
Yeah, so actually that's what I was going to ask, that there we use disorder as a central feature to explain the letters and so on. And here, is it roughly in our thinking that the interactions are more important than the disorder?
These two are going to flip around. We'll still need disorder, but it's important that the interactions and the disorder.
Related to his question, this picture you drew with this blob with the central line, so what are the Chern numbers? How do they work? I mean, the answer you got was a sum over Chern numbers of occupied bands, right? For sigma.
With the central, sorry, which picture?
So, you do this Landau band getting broadened. This picture with the center. Yeah. And then, so what's happening to the Chern numbers?
The Chern number, so you have a bunch like this. And as you vary EF, remember the Chern numbers can't change
unless you
as long as you have an insulating state, as long as there's a gap.
Right.
And so the Chern number is 0, 0, 0. Here it's poorly defined because there's no longer a gap. And when you go here, it's 1. And then it's 1, 1, 1, 1, 1. Here it's poorly defined, here it's 2.
Okay, so in terms of the formula you wrote down, it was a sum over average. it's the average of all the occupied terms.
That's the sum over all.
Sum over.
For the lattice picture, not quite this, but for the lattice picture, it's the sum over filled bands.
So what Sandeep is saying is the Fermi energy is somewhere in the middle between the two blobs.
Fermi energy is not relevant here. Fermi energy is...
No, but you have to decide which ones you're going to count as filled. Right? So the plateau phenomenon...
Fermi energy is not one of these three. That's
I know, but in the plateau phenomenon, I guess you're changing EF and the numbers remaining a constant, sigma xy, then it's average. So
the middle point is where you are jumping from one.
So you jump when...
EF is here.
It's here.
So it was 0, 0, 0, 0, 0, so sigma xy is 0.
Yep.
Then you went through. And then there are some which have Chern number 1, and then there are more occupied states below that have Chern number 0, right? And then you're going to sum over all the occupied states?
I'm not quite sure which...
So you derive
we just want to distinguish between... There's so many geometries here. So
the formula you derive in
Yes.
terms of sum over occupied bands or occupied states.
So that was for the lattice.
Right.
And I think we agreed that we shouldn't use that formula.
But there's some version of that formula that applies here.
So the formula that applies is the other one with the spatial torus,
Which also defines some Chern numbers.
which also defines...
And the answer is again sum over occupied states instead of occupied bands?
No, because it's not a single particle phenomenon in that.
No, but if I have
just
single
the-
particle with disorder, which is what this is.
on the torus,
Yeah.
then that would be right. Here there's no gap. And yes, it would be
Right.
0, 1...
So now the formula says I add up Chern numbers of all the occupied
there's
states? No.
Oh.
Isn't that what?
No, the Chern number in that case is not associated to each band. The Chern number in that case is just associated to the state full stop.
It's state, right?
Oh,
Yes.
I see.
So every state has a Chern number?
No.
No.
There's a state.
Oh. Anybody.
It's many body ground state.
Okay. Thank you.
It's associated
Thank you.
to the many body state.
Thank
not
you.
the single
Okay.
I see, okay.
Thank you.
That's it.
Otherwise,
I could see the contradiction you
Yeah.
Okay.
Thank you.
I'm glad I warded off the contradiction before I saw it. All right. So what do we expect? So it's pretty clear it's going to be hard to solve this. But let's just think about what we see experimentally and how we can reconcile that with the sort of things that we would expect from general grounds. So we expect the following. That, let's look at the Landau level, and this is the density of states. And let's just look at a single lowest Landau level. And let's think about the effect of this interaction. And we'll assume just that the Coulomb energy is much smaller than the gap between the Landau levels, which means that these states here are not going to mix with the next Landau. So I'll just ignore those. So what we expect roughly is similar to what we saw disorder would do. There was degeneracy, you add an interaction, it lifts the degeneracy, so you expect that this gets spread out. We still have translational invariance, so we don't expect to have this separation between localized and extended states. But we do expect these to be spread out. How could we explain the fractional quantum Hall effect? We could explain it if, in this spreading out, at very certain fractions, a gap emerged. So if at 1/3 filling, supposed to be 1/3 of the volume up, there was a gap with no states in that gap. Okay? How would that explain the nu equals 1/3 Hall effect? Well, we'd fill up to here, and then we're very much in the situation we were in with the integer quantum Hall effect. There's going to be a gap to excite the next particle. We'd have exactly the right quantization because we filled up 1/3 of these states. To really argue that you get a plateau, we need to use all the same kind of arguments that we had about disorder, and disorder giving rise to some extended states in here, and maybe so that somehow you can vary the chemical potential and keep those number of extended states constant. To my knowledge, that understanding of disorder in the interacting case just hasn't been done at all. I think that's way too hard a problem, but it's clear conceptually that it could work the same.
Except that the size of the gap here would be much smaller than.
So you need now to be in the regime. The separation between Landau levels is much bigger than the Coulomb energy. The Coulomb energy is going to dictate, I think, both this spread and the size of this gap. But obviously, one is smaller than the other. And then disorder is. Which explains something experimental. It explains that it's only when you go to cleaner and cleaner systems that you start to see the fractional order. Because this disorder energy has to be much smaller than the.
Sorry, what is this gap again? I mean, the idea is you have one extended state.
No, so let's forget about disorder for now. The idea is that when you look at the density of states, it's not nice and smooth, but there's a gap.
Interaction.
Due to interactions. And then there's going to be another gap at nu equals 2/5. But the gap at nu equals 2/5 will be smaller than the gap at nu equals 1/3, precisely because you need suitably cleaner samples to see the 2/5. There will be another gap at these stupid fractions. At 3/7, and another gap at 4/9. And then the gaps become progressively smaller as the plateaus become more and more delicate and harder to see. So that's kind of the vision that people have that would then explain what's seen experimentally.
I mean, the gap doesn't need to be order of equilibrium, no? I mean, in principle, it can have something like a superconductor where the coupling, it's not the coupling, it can be much smaller than the coupling, the gap that you are generating.
So there's only one scale in the game, so it has to depend on this. You're saying that it could be suppressed by some number, and that number could be exponentially small, but I'm not sure exponentially small in what.
Yeah, so this Coulomb over LB will give you always a scale for.
LB is the same as this.
This for omega 3. Yeah, so I'm saying
you just want to ignore those effects completely, because that's to do with mixing with the next Landau. So I think that this and this have to be parametrically the same, but with some.
He's saying if you do a calculation in the projected Landau,
then there is
only one energy scale. Every energy you calculate in that problem will be set by that.
And maybe this is 1,000th time that, or 100th time, or 100th of that. I'm not sure, but it's.
Doesn't it come back to the degeneracy of 2 pi LB square?
I think the only scale in the game is the Coulomb.
And sorry, can I just ask again a remedial question, which is, are these things metals before we start turning on magnetic fields and so on, or not?
I'd say yeah. And they're in a magnetic field, but yes, if you like. They're like a metal in a magnetic field.
No, normally in metal always there's this question, right? What about the Coulomb energy and so on? And then I mean, we're all conditioned to say, oh, if you're at the Fermi surface, some Landau Fermi liquid theory, blah, 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 something condensed matter words, and forget the deal. Dress it or whatever and forget it. Now here, why can't I say those words?
I think it's
I'm sorry.
Kinetic energy.
yeah. I think
The
that's
usual argument doesn't go through.
yeah.
Usual argument compares EF to the Coulomb energy at a typical separation, right? And that's the ratio you look at. Here all states are degenerate.
EF is 0.
So in effect there is no spread in kinetic energy, so what will you compare it to? 0.
Is the fact that all states are degenerate still true when I put in the Fermi surface? I mean,
Disorder, you mean?
no, okay.
You say it's not quite. There's a degeneracy in momentum of space now.
Yeah.
You're doing 3-dimensional?
Yeah. Or
We could do
2-dimensional.
two. We could do two.
In 2 dimensions, I guess.
So there is a degeneracy which is just K.
Okay.
And that's it.
So
No, there's not a degeneracy. There's
not
a
a
unique ground state. Right. Again, this is an issue about multi-particle versus.
Okay.
There's a unique ground state. There are gapless excitations above that.
okay.
But there's a unique one of.
Yes. This is a unique state, right.
Yeah.
Okay, and then, just help me. So in that unique state, I now turn on a magnetic field. And now, I mean, it's not the case that the electrons of the Fermi surface, okay, they start going some orbits and so on. And it's that degeneracy we're
But now you've got to worry about this. So if you turn on a magnetic field, this side here, is very small. And when you make that magnetic field big enough so it beats the Coulomb energy, then you do get a quantum pulse. Because that's exactly what we have, right? Is a bunch of electrons free electrons moving around in the absence of a magnetic field, they pile up and form a Fermi surface. And in a strong magnetic field, they don't form this quantum.
So I guess the magnetic field becomes high enough compared to whatever would have been Fermi energy, etc., etc.
Weak
Then you
magnetic
go to
field
this
is
other
magnetic
part. Okay, thank you.
So in weak magnetic field, you will get this standard
Dihasman,
Yeah.
all that. And so that happens for a while, then the magnetic, and there we can neglect Coulomb interaction.
Coulomb.
They get dressed and all
Yeah,
fine. Then you go to this other regime, then we can't say all those.
I guess the problem is p square. The p square over 2m part of the interaction becomes a constant, exactly a constant in the high magnetic field. Right? And if something is exactly a constant, it's as good as not being there. So then, what are you going to compare e square over r2? Nothing. It's the spread in p square over 2m that you need.
Okay, so this is the basic idea. There's going to be a bunch of gaps here. I've only drawn one, but every one of these special fractions, there will be a gap in the spectrum. And the bigger the gap, the more prominent the plateau that you see in the experiment. The fact that these statements are true should be clear from everything we talked about before, all that disorder.
Have this been seen in the small scale material simulations that such gaps?
Yes.
There you go.
Yeah. Yes. But it's 16 particles, so probably there's gaps everywhere. But the third is special. Okay. So, what are we going to do? So I'm going to start by telling you about the work of Loughlin, which I think it's fair to say that there's been a lot of work on this, but this is the single most important step in understanding the fractional quantum Hall effect, and it's what Loughlin wanted to know. So Loughlin described, or we follow him, described states at filling fraction mu is 1 over m. And we'll describe these states both for m odd and m even, but in the course of doing this, we'll see why the states with m odd are the ones that are relevant for experimental systems. So, firstly, it's clear that mu equals a third is the most prominent state, and it falls in this Laughlin class. In fact, if we take m to the odd, m1, of course, is just the integer quantum Hall effect. So this is the first of the Laughlin states. The others are, obviously a fifth, a seventh, and so on. They require very high magnetic fields to see filling fractions that small. And the fifth has been observed, but I'm not sure any of the others have. But the fifth is quite strong, I think, when you get to these high magnetic fields. So in principle, this is true for all filling fractions, but it's really a third that's experimentally the most relevant. Okay, so what did Laughlin do? It's quite astonishing. He was faced with this very, very difficult problem of diagonalizing a matrix which is e to the 10 to the 11 in size, and finding out what the true ground state is. And so what he did was just guess. Just basically pulled something out of thin air, in part because it was very easy to write down, and it turned out that it's not quite the right answer, but it's as close as the right answer as you could possibly have. So it's really a bold thing to do as a theoretical physicist. So we're going to explain what his guess is.
So what is special about the 1 over n states?
We'll
they have
see.
more prominent plateau or something? No.
Yeah. So the third has is by far the most prominent plateau,
Okay.
and the others.
So in general, the 1 by n plateaus are...
Yeah, but they're very high magnetic fields, so it's hard to get to them. So I think the idea is that if you were to get to those high magnetic fields, you would see these problems. And I think that's true for a fifth. There's many people know more than me about what experimental situation might be. Okay, so I'm not just going to write it down, I will motivate it a little bit. Laughlin motivated this guess in the following way. Firstly, he looked at the solution for 2 particles, and then he looked at the solution for 3 particles, and then he wrote down the solution for 8 particles. Which is quite a nice physics way to proceed. I'm going to give you the solution for 2 particles, and then I'll skip the 3 and just jump. So the motivation.
Sorry, I have to say, instead of doing 1, 2, 3 infinity, you did 1, 2 infinity explains 1, 3, 1 third. Sorry.
Exactly. So the motivation. Consider 2 particles interacting through any central potential. So a central potential, remember, is a potential where the force depends only on the distance between the particles and is in the direction from one particle to another. So how do we solve this? So we usually solve this whether we're in classical mechanics or we're in quantum mechanics. What we do is we separate out the center of mass motion, and then for the relative motion, we solve it using angular momentum. Because in classical mechanics, angular momentum is conserved, and in quantum mechanics, we just write down we try to figure out the eigenstates which carry the right quantum numbers of angular momentum. It's how we do the hydrogen atom. So we usually solve this working with angular momentum eigenstates. Okay, so for single particles, if we're in the lowest lambda level, we've seen what these are a couple of times. The single particle eigenstates are those states that have this wave function. So it's a holomorphic function, z to the n, and n is the okay, so if you just, this is going to be important, if you recall, this is peaked at a radius which is 2mLb. So the way you see this is you look at the mod squared of this, and you notice that this makes it want to rise away from the origin, but this kills it as you go far away, so there's some competition between these two, and it's peaked at precisely this value there. And this has angular momentum. So the angular momentum operator is h bar d minus z bar d bar, and acting on this state, it's just equal to h bar. Okay, so what about the two particles? So the two particles, what do we want to do? So we separate them out into the center of mass and the relative position. The center of mass is going to be trivial. The center of mass in a magnetic field with two particles is just going to do this. Okay, so there's some overall angular momentum of the center of mass. More interesting is what the relative particles are doing. So the eigenstates are okay, so there's something quite remarkable that happens here. The eigenstates, now eigenstates are two particles. The center of mass is just a statement that the whole thing can classically move around. So this is the total angular momentum. But if you restrict to the lowest Landau level, there's a unique eigenstate that has a particular relative angular momentum, which is this. Okay, so this is amazing because this is the eigenstate for any potential V of R. So the eigenstates are for any V of R1 minus R2. Now you wouldn't dream that this would be the case in the absence of a magnetic field. Right? The eigenstates of the harmonic oscillator are not the same as the eigenstates of the hydrogen atom. But if you're in a very large magnetic field, these are the eigenstates regardless of the potential, as long as you're restricted to the lowest Landau level. So as long as this is much smaller than this. Okay? And the reason is simple. The reason is that you want to write down an eigenstate that has relative angular momentum, little m, total angular momentum, capital M. But when you're in the lowest Landau level, holomorphy basically says that there's a unique such state. So this has to be the eigenstate whichever potential. It's really a striking point.
But I mean, is it? It's not the same as saying when this condition is met to zero, thought I can neglect the potential, and this is the
no, because the potential is important. Otherwise, the energies of this, of course, will depend on the potential, but the eigenstate.
Then at second order in perturbation theory, the state will shift, right?
So there'll always be corrections of h bar omega b over this, and they're mixing with the higher Landau levels, and they'll depend on details. But to leading order in, as long as the gap between the Landau levels is, this is the unique height. It's really surprising.
Yeah, it's very surprising. And M is just fixed by which Landau?
No, so we're always in the lowest Landau level.
So
capital M is the total angular momentum. Little m is the relative angular momentum. So if we want to just think about these things sitting there and not doing this, just set big M to zero. That's what we'll do. These are the eigenstates.
And they are in the lowest Landau level for every value of little m.
Yes, because they're holomorphic.
The energies will depend on the choice of
Energies depend on this, yeah. Okay, so we've not done any calculations, but we know just on general grounds this has to be the eigenstate for any potential. There's another surprise here as well. Suppose you have a repulsive potential. Then usually when you have a repulsive potential, you don't get any bound states at all. Right? Because things get get pushed away. But now we see we have a discrete spectrum even with a repulsive potential. So even if you have a repulsive potential, you get bound states. And again, it's because magnetic fields make things do this. So everything is sort of trapped by the magnetic field. So it's a very surprising result. Much simpler than anything we know from the Okay. What about for many particles?
So what m is the ground state depends then on. So if I want to know what's the lowest energy eigenstate, these are all the eigenstates.
These are all the eigenstates. So roughly speaking, the potential is V of R. This wave function is peaked on this. So the energy Em is roughly speaking going to be V evaluated at this. Okay. So if you have a repulsive potential, let's say the Coulomb potential, it looks like this, then the energy eigenvalues are roughly going to be these.
David, can I come back to this statement? Is it more than perturbation theory? That is, let's define a parameter epsilon, which is the ratio of V over H bar over.
Yeah.
Then to zero it, order in the parameter the ground state is that neglecting V. And then there is a correction to the energy.
Yes.
Or at order epsilon, which you compute by just computing the perturbation.
Yeah, but that's an energy. That's order epsilon to the zero.
Say that again.
So your epsilon is
V over
H bar over V.
Right.
So the correction to the energy is at order epsilon to the zero.
Oh, it's not.
This is degenerate perturbation theory, so you're finding the right basis, right?
Yeah.
That's all you're doing. And that quantum numbers are helping you do.
So you're saying
But you can see,
Are you asking
this is the energy.
No, he's not.
You're not.
So this is the energy of these states, roughly. Sorry, should I do that argument again? It's a nice argument, so maybe I should say more clearly.
So, but just since this came up, you're saying the degenerate perturbation theory that the ground state is determined. I'm still missing something. What's fixing M?
Nothing.
These are all the states.
All the.
These are all the states.
So here's this argument again. The energy. It's kind of the same classical argument. It's V to the R. But in the wave function with little m, R is approximately equal to 2m LB. So the energy of the mth state is roughly the potential energy you put in, evaluated.
And you're saying, although this formula for the energy is an approximate semi-classical thing, the fact that that's an eigenstate is exact, right?
Exactly.
Yeah.
Well, up to
the mid-state. Yeah. At epsilon to the zero, it's exact.
Non-triviality is because it's highly degenerate, but you're still sure.
That's why it's surprising.
You're saying
But
because
it follows on general grounds, right? Because
just quantum
you know the
numbers.
eigenstates have to have angular momentum as a good quantum number. These are the only states with angular momentum.
So in this basis there are no off-diagonal
Exactly.
There are no off-diagonal elements because this is central potential.
Exactly.
So you cannot mix different angular momentum eigenstates. So
That's right, exactly.
That's
Central
right.
was required, so you had angular momentum.
So there are only diagonal eigenvalue, and that's
Yeah.
All right. So what do we know about for many particles? It would be really nice if you could just use these arguments to write down wave functions for many particles. It doesn't work. Of course, it doesn't work. You only have one conserved quantity, which is relative angular momentum, and you have many particles. You don't have relative angular momentum between each individual pair. They don't commute with each other, so we don't get to use this. So for many particles.
But he could solve the three-particle thing exactly again?
Do you know,
Epsilon to the zero?
I'm not sure. I think he was using a little bit of numerics and a little bit of, I don't think it was an exact solution. It would be very surprising if it was an exact solution. So the best we can say is that the wave functions takes the form. If we're in the lowest Landau level, it's just some holomorphic function. And we know that if they're fermions, this should be antisymmetric. X and fermions, and it should be symmetric. So based with this intuition, and not too much more, like I said, Laughlin did do the three-body problem. Laughlin just guessed the answer for the graph. This is Laughlin's guess. So n particles. This is the Laughlin wave function. Okay, if m is odd, it's antisymmetric. If m is even, it's symmetric, which means that if m is odd, this is the wave function which describes fermions. And if m is even, this is the wave function which describes fermions.
So already for three bodies, it's very non-trivial, right?
Very non-trivial.
But is it true? Is it exact?
No, it's not. It's not exact for anything. Okay, I'll make a few comments now about but firstly, just for the high-energy physicists, if we were faced with this problem, this is something we wouldn't dream of doing. Not just guessing, but writing down a wave function. It's something we never do in high-energy physics. Instead we'd have done what condensed matter people later did, which is think about some effective long-distance theory and write down Chern-Simons terms. Lots of brilliant stuff. But writing down a wave function is just, wave function is something we do in second year undergraduate, right? And then you forget about it. And for the condensed matter physics, all the great breakthroughs, most of them came from guessing wave functions. And it just feels that maybe we should take this lesson on board in high-energy physics. That maybe if we're doing quantum field theory or something that seems complicated, they just guess a wave function. I don't think anybody's ever done. It's so important in this area.
I have to interject. Since you come from Cambridge, your illustrious colleagues have guessed the wave function of the universe.
Yeah, but
how about that for modesty?
Getting the right answer is important.
No, that's another matter.
Okay, so let me tell you about this wave function. So Laughlin guessed it. It's not right. It's not the exact ground state wave function. Because why should it be? It turns out that for a small number of particles, it's extremely close to being right. So as I said, you can diagonalize these matrices for particles roughly up to 20. I think a little less than 20. And it turns out that for this number of particles, this wave function has 99.9% overlap with the true grounds. Okay, so it sounds very impressive. This is true regardless of the repulsive potential that you put in. Put in the Coulomb potential, 99.9% overlap. Put in some exponential potential. Put in any random repulsive potential. This is good. Okay, so yes, please.
But for n equal to 2, we don't have the 7 plus n plus 2.
Sorry, you don't have the...
For n equal to 2, we had 7 plus n plus 2 and n.
That's right. So there's that was sort of the whole system doing this in space.
Yeah.
And the ground state is always going to be just setting that to 0. The total angular momentum is... It's like if you're in solving the Schrödinger equation for a hydrogen atom, you don't worry about the overall translational motion. Right? That was the analog of translational motion. So we'll set that. So it looks very impressive, and there's a huge part of the community who spend their time diagonalizing various quantum Hall effect wave functions and checking that their guesses are good. Again, I'm not an expert, so you should take this with a pinch of salt. It strikes me that this is really unpopular. Because, okay, it's 99.9% for 20 particles. As far as I can tell, that means that when you get to the 10 to the 11 particles, it's 0%. Okay, because it's that 0.01 that just gets bigger and bigger and bigger as the Hilbert space gets huge. So yes, you can just jump up and down and say, look, it's so good for 20 particles, but it's just rubbish if you're looking at 10 to the 11 particles. So this can't be the reason that this is a good wave function. You know, there has to be another thing.
But how do you know it doesn't get better?
That's what I was going to ask. Yeah.
Why would it get better? The Hilbert space gets vast. The Hilbert space grows exponentially. So the amount of ways you can miss is so much larger.
No, but isn't it true that you can construct certain repulsive pseudo-potentials which have this as the exact answer?
We can construct a Hamiltonian for which this is the exact ground state.
In the large number of particles
for any number of
I see.
Yeah. It's completely artificial, and it's cooked up by basically looking at the properties of this and then writing down a Hamiltonian.
But it's some sort of repulsion between them.
Yeah. So I think this is probably a more important fact. Is that this is the ground state for some kind of local Hamiltonian between the electrons. And I'm not decided it. It's in the notes. Maybe we'll discuss it in the lectures depending.
And in that case, it's exact at any finite number of particles. It's not like it gets better and
that's right. It's a totally artificial Hamiltonian that's just designed to have this as its.
But if you just took a generic, let's say you took the Coulomb potential itself, you say that actually this will do less and less well, is it?
Do you know, I have to say, I've not seen this written down, but it just seems it must be less and less well, because the sample space is enormous.
One way of thinking.
There's some intuition of holomorphicity plus I don't know what.
Everything's holomorphic. But it's known that it's not the true ground state. Right? It's got. Let me tell you what I think is important about this. First, you can see why it does well. It does well because whenever you have a repulsive potential, you don't want the particles to come close together. And it does well because when the two particles come together, okay, it gives 0, but it had to give 0 by Pauli exclusion, but it gives 0 to some large matter.
So hence, as you increase the number of particles, there are many more ways you could have constructed total angular momentum. Whereas with 2 particles, this is only very good.
So I don't think it's the fact that it agrees with numerics. That's right. I should say that. Actually, let me first tell you what is good about it. What is good is that it's in the right universality class. So what do we mean by that? Usually we talk about universality classes in terms of RG flow and theories flowing to the same critical point. So you start with 2 very different theories, liquid, gas, and an Ising model, and when you get the critical transition, the physics is identical. So it's in that same spirit that there's many different wave functions you can write down that capture the same physics, where the physics that's relevant here is very exotic things like the excitations above this wave function carry fractional charge and fractional statistics. Mm-hmm. Or if I was to take this wave function and consider it on a spatial torus, or a manifold of different genus, then there's a number of ground states that appear that depends on the topology of that manifold, and that's captured in this. Mm-hmm. So it kind of has topological characteristics that are the same as the real wave function. Mm-hmm. I think we could probably also talk about entanglement, the entanglement that's inherent between different particles in this is somehow the same as that in the real wave function. So that's really what's special about this, and the fact that it agrees numerically is, it's convincing, looks very good, but I don't think it's the thing we should be jumping at.
If I go by what Azli just said, that the general choice is Ki minus Dj to the power Mij.
Yes, it is this way.
So in the space of all these Mijs, clearly all Mijs equal will have the largest entropy.
No,
I mean, in the sense that let me take the the binomial formula for how many what's the distribution of Mij.
Nice, but different particles.
So in that, I think I do know this. I mean, this is what happens with this long string counting. All images being equal. That's like this, all these long strings. I can say that all images being equal, I think, is the largest exponent. See, I have seen.
Given that all the particles are indistinguishable, is that?
Yeah, I'm saying that, so the sum of all images,
Yeah.
it has to be the total angular momentum.
Yeah.
Okay, so there has to be multinomial formula like, whatever, total angular momentum, factorial, divided by all the images, blah, 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 factorial. Okay, and And then I think all the MICs being equal,
assuming
all
the
approximately
pairwise
equal,
function.
should be the largest.
What I'm talking about assumes the pairwise function.
Maybe explain it to me.
Sorry, but before you go on, can I ask, just like when BCS wrote down that famous wave function, there was lots of stuff to come, deduce experimental consequences and then check against Amtor, right?
All the next lectures will be coming up with predictions for this, experimental consequences.
Okay,
so it works.
It works.
So for anything you would care about, this is the right way.
Sorry, David, I didn't understand this MIJ comment that several people made. It sounds to me like if I actually do permutations, will that not scramble up the MIJ?
So you can't quite just have all the MIJs independent.
I mean, you need a Slater determinant of that function.
So you can't just write MIJ. Okay.
And sure, at least.
So what this really has is the relative angular momentum for each particle is always greater than or equal to m. That's what's special about this. And in fact, that's how you construct those two-way Hamiltonians, is just projecting out those states with angular momentum less. Okay. But by the way, I've been knocking these numerics. One type of numerics I think is good is when people have two candidate wave functions for different filling fractions, and the candidate wave functions are in different universality classes. And then you want to know which one of those wins, and that's often a very detailed issue about what dynamics is doing. So the numerics is useful for that, but the fact that it's good for this, it's probably my bias.
Also, if they've done numerics from 12 to 20, the Hilbert space has already increased enormously.
It's true, it's still impressive that it works on 20. Yeah, I agree. It should be possible to see if it's going down or up. I'm amazed if the overlap's going up. Okay, how are we doing? The next thing to do is to compute the filling fraction. It's only about 5 minutes. Shall I just... People have the energy for another 5 minutes? You sure?
As long as you have it.
Alright, so to compute the filling fraction.
I'm really sorry, but can I ask you one more question, which is there a variant of SUSY quantum mechanics close to your heart? This question, I think, many body version for which we could write down this answer.
My seminar on Monday, I'm going to give quantum mechanics matrix model, whose ground state actually doesn't have this wave function, but has the wave function which looks like this on long distances, but differs on short distances. But it, again, is in the same universality class. So my claim is just as good as this. For SUSY, I've thought of because it's hollow. It smells like it. I've never made that fly. The matrix model I wrote down came from SUSY, but it turns out it's actually just a prototype matrix. Okay, so how do you compute the filling fraction? Well, what you do is you figure out the area of the droplet described by this wave function. So we have n particles. So what do? You focus on one particle. Look at just, say, Z1. So you think about Z1 as being dynamical and all the other particles' position just being fixed. Okay, so it's a wave function just for one particle. Note that the maximum power of any position, but let's say Z1, is Z1 to the power m times n minus 1. Z1 can multiply the n minus 1 of the particles, then the whole thing raised to the power. Which means that the maximum angular momentum of Z1 is m times n minus 1. But remember, these wave functions for Z1 with higher angular momentum, they have higher and higher concentric rings. So the size of the droplet is going to be the size of the wave function with this largest angular ring. That's as far as this wave function spreads. So the droplet has an area pi times the r squared, where R was this thing which was the square root of 2m. Sorry, the square root of, my bad, the m's are different. It's the square root of 2 times the power of z. M times n minus 1 LB squared. Which is 2 pi m n LB squared. Where I replaced 10 to the 11 minus 1 with 10 to the 11. Okay, so that's the area of the droplet. But the number of states in the lowest Landau level is just b divided by phi 0 times the area of this space. And just plugging this in, you get m times the number of particles. Okay, so the number of states in that area was m times n. Obviously, there's n particles, so the filling fraction u is 1 over n. Okay, so already we see something, learn something about the experimental data. We learned that with m odd, it describes fermions, and electrons are fermions, so we should only expect to see filling fractions with 1 over m odd, not 1 over n, which is exactly what.
Sorry, that went by me a bit fast. I got till there. The droplet has this size.
Oh, good. So the droplet has this size. So the number of states you could fit in a Landau level of that size is m times this, which is m times the number of particles we put in there. So the filling fraction is the number of particles divided by the number of states. Number of particles is n divided by the number of states. Filling fraction is 1 over n.
I'm really sorry, please forgive me. I understand that the total number of... So the droplet size is this.
Yep.
And, but I mean, you're more than one particle in the same droplet, right?
Yep, I've got n particles in there.
You've got
n was the number of particles.
n droplets in that size.
N
particles.
N particles.
This was a wave function for capital N particles. And the size of the wave function we computed was an area of this size. So how many states in the Landau level of an area of this size? Well, it's this, which is m times the number of particles in the droplet.
Okay.
So 1 in m of those states is here.
I see.
Okay, so just to repeat, the wave function was for fermions when it was odd, bosons when n was even. This says that if electrons are fermions, which they are, we should only see filling fractions with 1 over odd denominator, which is exactly what you said. So it explains this very simple thing about atoms.
To understand that equation, given a number of electrons, this is kind of a constraint on the magnetic field, is it? The magnetic field has to be just, for a filling fraction, the magnetic field has to be tuned to a certain value.
No, well, what do we,
It cancels out.
Yeah.
cancels out because the magnetic field comes here. If you have a stronger magnetic field, the area is bigger. Right? There's an LB which sits in here which has the magnetic field. So if you have a stronger magnetic field, the area described by this droplet is bigger. You can also see it's in the exponent. The exponent is e to the minus mod z squared divided by LB squared. 4 LB squared. And LB is the magnetic field. So you can see explicitly there, as LB changes, the thing is getting bigger or smaller. But the density of particles is remaining the same. So density meaning filling fraction. Yeah. Okay. Any questions about this? So the next thing to do, which we'll do on Friday, is start computing. Start taking this Lofton wave function, understanding its consequences, understanding what it means for this droplet, thinking about excitations of this droplet, all the lovely physics that's contained in this. Okay. See you Friday.